So today what I'm going to be going over is basic linear momentum. So first of all, what is momentum? A lot of people describe momentum as the movability or the stoppability of an object. So what does this momentum depend upon? Well, momentum depends on the mass of the object that's in question and the speed or the velocity of said object. And because momentum is a vector, we will be looking at the velocity of the object. Alright, so to get our basic equation for momentum, we have P, which is the symbol for momentum. Alright, I'm going to write that. P equals the mass of the object times the velocity of the object. And for a simple equation, we can get the mass of a car, which is about 3,000 kilograms, and then get the velocity of said car, which we are going to say is about 45 meters per second, and multiply those two together, the mass and the velocity, which are in kilograms and meters per second because momentum is in kilograms meters per second. So we get the momentum to equal 135,000 kilogram meters per second, and those are supposed to be multiplied right here. And that's how we do a simple problem to get the momentum. Although most problems will require you to do this, it will be more involved and a lot more difficult. That's just very, very simple example. Alright, so the way what I just showed in the video can be useful is whenever we talk about conservation of momentum. In a system, conservation is always, always, always conserved. So the momentum just before and just after a collision are always equal. So the way we can sort of explain this is talk about a clay ball hitting a soccer ball and sticking to it. The momentum of those is going to be equal. So I have a couple of variables that I have set up right now. So we can think of P final equals P initial. So, or P initial equals P final. So what we have for our initial is going to be for our M1, which is P initial is going to be M1 times V1 plus M2 times V2, because momentum is mass times velocity. And then our final, we're going to call it M3 and V3. Alright, so our M1 is going to be 2 meters, or 2 kilograms. I'm going to leave off the units, and I'm going to add them at the end because it's going to be more simple. Times 50 plus 10 kilograms times 0 because the basketball is at rest. So the question is, how do we get the velocity of these objects after the collision? Because they stick, they're going to have, the masses are going to be the total of the two masses. So our mass is going to be 12. And then it's simply solving for variables to get V3. So what we do on this side, we multiply both. This one's going to be 0, this one's going to be 100. So we have 100 right here. And then we have 12 times V3. So, because this is kilograms meters per second, and this right here is going to be in kilograms, our kilograms are going to cancel, and we're going to be left with meters a second, which is velocity. So our velocity of the total, or V3, is equal to 100 over 12 meters a second. And that's how momentum can be useful, because it gives us the ability to find the velocity of objects after collisions have already occurred. Alright, so our next major component of linear momentum is going to be the difference between inelastic collisions and elastic collisions. Elastic collisions typically occur when objects bounce off of each other in collisions. In this, momentum is conserved, and kinetic energy is also conserved, so the kinetic energy initial, 1/2 mv squared, is equal to the kinetic energy final. In inelastic collisions, you're going to have the objects stick together typically, and it is going to be whenever the momentum is conserved, as is in all collisions, but actually the kinetic energy is not conserved. So I'm going to use our problem here. Because these two stuck together, we should get one that gives us kinetic energy that is not equal to the kinetic energy final, but we're going to go ahead and demonstrate this. So kinetic energy final is equal to kinetic energy initial. So we do 1/2 mv squared plus 1/2 mv squared of object 2 is equal to the final, which is 1/2 mv squared. And we fill in our variables, which is 1/2 times 2 times 50 squared. That is a 50, I promise. Plus 1/2 times 10 times 0 squared. And that, since it's multiplied by 0, is going to cross out, so we do not need to worry about that, times 1/2 times 12, which is the two combined, times 100 over 12 squared. And for this I'm going to use a calculator because I don't want to mess up any equations or any numbers. So I'm going to do 50 squared times 2 divided by 2. And that is going to give us 2,500. And then we do it for the other side also. I do 100 over 12 squared times 12 divided by 2. I get 416.666 repeating. So obviously these two do not equal, so this is an inelastic collision. Alright, so now for one of the most important parts of linear momentum, impulse. Impulse is able to be seen throughout our everyday lives in cars. Whenever somebody gets into a car accident, airbags don't really decrease the force that is applied on a person, but rather increases the time, so the impulse increases. This can be shown through the formula for impulse, which is J equals, and the J is impulse. J equals the net force times the change in time. Force does not change whenever somebody gets in a car accident due to an airbag. All the airbag does is increases the time, thus increasing impulse, which is the change in momentum, causing it to not hurt the person as much and save the person's life. We have a graph with force on the y-axis and time on the x-axis. We can find the area under the curve to find the impulse. So these are the basics around linear momentum. Although they can get more complicated and more involved, if you're able to do these, you should be good.